Now the second type of special functions that we want to take a look at are the step functions. Now, the step function basically comes from a thing called the greatest integer less than or equal to x. So let's take a look at this. F of x is equal to the greatest integer less than or equal to x. Now, there's a couple of things that you have to know to be able to understand these functions. The first thing is what an integer is. Now remember, integers, and we use the capital Z to stand for integers, are the set -3, -2, -1, 0, 1, 2, 3, and so on. Integers are any number, positive or negative, that has no fractional or decimal part. Now, the idea of a step function is this. Let's actually take a look at some values for x and f of x. And then we'll take a look at where they line up on the graph. For example, let's put 0 in for x. Now, if x is 0, then the greatest integer that is less than or equal to 0 is going to be 0. Don't slam. Would you kind of hold the door and don't let it slam? Thank you. Now, if we try a number like 1/2, the question is, what's the greatest integer that's less than or equal to 1/2? Well, now, 1/2, if we take a look at the number line, here's 0, here's 1. 1/2 would be here. Now, the greatest integer that would be less than or equal to 1/2 would still be 0. If we try 2/3, the greatest integer that's less than or equal to 2/3 is still going to be 0. The greatest integer less than or equal to 9/10 is still 0. The greatest integer less than or equal to 0.999, now 0.999 is really close to 1, but it's not equal to it, so we have to go down to the next integer, which is still 0. But as soon as we get to 1, the greatest integer less than or equal to 1 is 1 itself. So if we were to look at this on a graph, what we would end up doing when we were plotting these numbers, we'd have, here's 1, here's 1. We'd have 0, 0. We'd go to 1/2, we'd still be at 0. We'd go over here to 0.999, we'd still be at 0. But when we actually hit 1, it jumps here. Now, after it jumps, it stays at 1 until we get over to 2. And see, the greatest integer less than or equal to 1.99 is still 1. But as soon as we get to 2, the greatest integer less than or equal to 2 is 2. So it would jump again, and then we would stay at 2 until we get over here to 3. And once again, it would jump up to 3 this time. And then it would stay there until we get to 4. And so notice what we've got here is something that looks like a set of stairs, which is why they call it a step function. Now, I like to try to give my students a picture to help them understand what's going on with the greatest integer function. And so let's do this. Imagine, if you will, that you have a number line, and this number line is actually a wood board with nails sticking through it. And we're going to number these nails. -2, -1, 0, 1, 2, 3, 4, 5, etc. Now, just a second while I make sure all of this is grouped together. Yeah, that didn't group them together originally. So there we go. Now, what we're going to do is we're going to tilt this number line so that it goes down like this. Now, when we take an integer, or when we take a number and we throw it at this number line, if we put it here at 2 and 2/3, what's going to happen to this? Well, it's going to slide down the number line until it hits a nail, and then it's going to stop. So the greatest integer less than or equal to 2 and 2/3 would be 2. Now, same thing over here. If we have -1/3, the greatest integer less than or equal to negative 1/3 would be what we get, when, come on, the number's supposed to slide, number line's supposed to stay the same. It would run down till it hit the first nail, and it would stay there. So the greatest integer less than or equal to negative 1/3 would be negative 1. Now, what if we actually put a number on, say, 4? Would that slide anywhere? Well, no, because it's already at a nail, so it would be stuck there. I'll be back in a moment. Hello, I'm back again. You may not have missed me, but I was gone for a few minutes. Now, the third function, special function that we want to talk about is the absolute value function. Now, the absolute value function is one that you are aware of already. F of x is equal to the absolute value of x. Now, what we'd like to do is we'd like to define that using a piecewise define function. Now, you know from absolute value that any time the number inside the absolute value is not negative, that you just get the number itself. So the absolute value of x, we would say, well, it's just x if x is greater than or equal to 0. But now, when the number inside the absolute value is negative, another way of saying negative is less than 0, then we take the opposite of it. So we would say the opposite of x if x is less than 0. Now this takes a little bit of looking at to kind of understand. See, notice here what we're saying is that we're actually applying a negative sign to a number when we pull it out of the absolute value. But what we're really saying is that if the number we pull out of the absolute value is less than 0, in other words, if it is negative, then we take the opposite of it. That's what that right there says, the opposite of x. Now, the absolute value function, because of that, treats numbers as if they're in two different classes. In other words, whenever a number is not negative, it leaves it alone. It's just transparent. Whenever a number is negative, it changes its sign. So if we were to look at the graph of the absolute value of x, let's just put x on this row and we'll put f of x on this line right here. All the numbers of 0 and to the right of 0, we would just say f of x is equal to x. So that would be the line y is equal to x. But now, whenever the number is less than 0, we would take the opposite of it and we would get something like this. So notice the absolute value of 1 is 1, the absolute value of 2 is 2, the absolute value of 3 is 3, the absolute value of 5 is 5. That makes sense. The absolute value of 0 is 0, so we get the point 0, 0. The absolute value of negative 1 is 1. The absolute value of negative 2 is 2. The absolute value of negative 5 is 5. So notice that this side of it makes sense also. Now, once we start doing things with inside the absolute value and outside the absolute value, this will be moved around and maybe transformed some, but this is the fundamental nature of an absolute value graph. It has a sharp bend in it somewhere. Now, if you are ever asked to graph an absolute value function and you don't find the sharp bend, then that graph is going to disappoint you, because there is a sharp bend someplace and you need to find it, or you will not have all that you need to have there. All right, once again, just remember that the only place where success comes before work is in the dictionary. And we're done.